We'll begin with a couple of announcements. First of all, this is the lecture for class number 19 on the 29th of October. Remember that homework 5A, which includes a set of problems from chapter 5 in the book, is due on Tuesday, the 5th of November. On problem number 38, please make sure that you explain why or why not for each of the responses that are an option. That's a problem with multiple parts, and I'd like you to basically explain your answer. Do more than just say yes or no to each of them. On the experiment design lab, the handout is due today by noon, meaning that you should upload that handout that you prepare to MU Online by noon today, the 29th of October, and then the report is due on the 5th of November, meaning that you have until Friday of this week to complete the lab, and then until Tuesday in lab to prepare the report. Following homework 5A, the next homework assignment 5B includes the set of problems that are listed there, and it's due on Thursday the 7th of November. And you'll notice that that's just 2 days after homework 5A is due. And the reason for the short turnaround there is I've actually extended the deadline for homework 5A so that you're getting a little bit more time to do that. And so I would encourage you not to wait necessarily until Tuesday to begin looking at that second set of problems, which is 5B, but you can begin on those immediately. There's no sense to delay. It's just that I've extended the deadline a little bit for homework 5A. So today we're going to be continuing our discussion of control volume approach and continuity, and looking a little bit more into the Reynolds transport theorem and how it's applied. Just to walk through what it means is that you can break the expression into two parts, assuming that the mass in the system is constant over time. What we'll assume is that inside of a control volume, that the system is not creating mass or destroying. It's not a chemical reaction that we're working with when we generally have fluid flow problems, and so the mass of the system isn't changing over time. So we set dm dt equal to 0. The total number of particles stays the same. And so therefore, if we consider a control volume, what's inside the control volume will either accumulate or there will be a reduction in that amount that's inside of the control volume over time in response to the flow of mass through control surfaces. And so CV here stands for control volume, and if you can think about an imaginary enclosure, you can place that enclosure anywhere, and you can look at the flow through the control surfaces, CS, and considering the flow through the control surfaces, there will be the velocity that flows through the surface and the differential area through which that velocity is flowing. Density is present in both of these terms, both the accumulation term and the transport term, because what we generally do is consider mass as being conserved. And so if we take a volumetric flow rate, cubic meters per second, and multiply that by the density of whatever fluid is flowing, then the units are kilograms per second, for example. And so over time, the change of mass inside of the control volume, dV, the change of volume multiplied by the density, we'll say a change in mass over time is in response to a net flow through control surfaces, the surfaces that bound that control volume. And essentially, we change that around to look like the flow of mass in minus the flow mass out in a system is equal to the rate of accumulation. So we're going to look at a couple of examples today where that principle is applied. But let's go back to basics a little bit and talk about why we use the Reynolds transport theorem and how. Some of the relationships that we learned in chapter 4, such as Euler's equation or Bernoulli's equation, really should be applied along a streamline. You'll remember that one of the assumptions behind Bernoulli's equation was that we consider the change in pressure and velocity for a particle in an incompressible, inviscid fluid with steady state conditions, but the key, one of the keys, was that it's along a streamline. And so in order to find a change in pressure between A and B, you can integrate Euler's equation between those 2 points or apply Bernoulli's equation if the flow is steady. But the problem is, in all Lagrangian techniques is that there's so many particles that to apply this to every molecule of water that's flowing through the system would be very computationally intensive. And so the Eulerian approach is to, instead of tracking individual particles, to divide the flow field up into elements and consider how flow is moving through an element. And in the Eulerian approach, you can develop a solution that allows you to characterize the flow properties at any point. And so an element is going to have a characteristic velocity, a characteristic pressure, and although there may actually be some variations of the velocity and the pressure in all of the molecules that are in that control, inside of that element, if the element's small enough, then there isn't a lot of change within the element. It's just as you go through the mesh, the properties change. And so the Reynolds transport theorem is a way for us to keep track of how the properties associated with mass flow through that grid. You can apply the free body approach to elements, considering the forces on the side of elements, or the differential pressure, and looking at how for a single element a change in velocity may give you a change in pressure. Keeping track of all of the changes over the flow field will allow you to apply concepts that we typically would require a Lagrangian approach, would allow us to apply Bernoulli's equation or Euler's equation to an environment that is mesh-based. So that little bit of fundamentals aside, let's consider a practical application of the Reynolds transport theorem. In this example, we have a tank that is receiving flow in, and there is a flow out, and we're going to try and solve here whether the fluid level is rising, the water level is going up, or if the water level is falling over time.
Alright, in this example we have a control volume, and inside of the control volume is a tank, partially full of water. There's a stream of water coming into the tank, and what we know is that the area of the cross section is 0.0025 square meters, and that's basically like the diameter, in consideration of the diameter, the area that can be calculated as the jet of water enters the control volume. We also know that the velocity where it does that is 7 meters per second. That is the velocity of the jet as it enters the tank. The tank is also leaking, and it has a volumetric flow rate out of 0.003 cubic meters per second. In this example, we want to consider the Reynolds transport theorem in terms of mass flow rate. And so the equation that we're going to be applying is consider the change of mass in the control volume with respect to time. And the way that we will do that is look at the mass flow rate in minus the mass flow rate out. So first we want to calculate what is the mass flow rate in. The mass flow rate in is going to be the density of the fluid times its cross-sectional area times the velocity in. And for this fluid, being water, 1,000 kilograms per cubic meter. And we know from the given information that the cross-sectional area is 0.0025 meters squared. And the velocity is 7 meters per second as it enters the tank. And so altogether that is 17.5 kilograms per second. Now we consider the mass flow rate out. Again, it's the density, area, and a velocity. In this case, the velocity out. So the the density is still 1,000 kilograms per cubic meter. The area here, we're going to actually combine these two terms. The area and the velocity is Q. What we know, Q is VA, and so since we're given the flow rate directly, then we don't know the area, the diameter of that opening, or the velocity of the water. All we are given is directly the volumetric flow rate out. So that's 3 kilograms per second that's flowing out. And so if you consider the accumulation, that's really what the Reynolds transport theorem is saying, is how much mass is accumulating inside of the control volume with respect to time. And so accumulation is what goes in minus what goes out. So dmCV dt is the mass flow rate in of 17.5 kilograms per second minus the mass flow rate out, 3 kilograms per second. And the net difference, 14.5 kilograms per second. So that's the mass flow rate of accumulation inside of the tank. What we're interested in is, for the tank having a diameter of 0.5 meters, then how quickly is the water level rising? Since there's an accumulation, the water level's going up, but we want to know how fast is it going up. So for a diameter of 0.5 meters, the cross-sectional area is pi d squared divided by 4, 0.19635 meters squared, if you pop that into your calculator. If the water level is rising at 14.5 kilograms per second, then we can find the volumetric flow rate of that. Remember, what we know is that the mass flow rate is the density times the volumetric flow rate. So if we want to know the volumetric flow rate, that's simply going to be the mass flow rate divided by the density. And what is the the volumetric flow rate of accumulation? We know that this is, what we could call this, is basically the mass flow rate of accumulation. That's how quickly the mass is accumulating inside of there. And so if we want to know at what volumetric flow rate is mass accumulating inside of the tank, then that would be 14.5 kilograms per second divided by 1,000 kilograms per cubic meter. And so therefore we get 0.0145 cubic meters per second. So the velocity of the water going up is going to be the Q accumulation, how quickly the water is accumulating, and then the cross-sectional area of the tank. So 0.0145 cubic meters per second, and the area of the tank we've previously calculated is 0.19635 square meters. So the water level is rising at 0.0738 meters per second. That's the velocity of the water as it goes up.
Alright, so we just solved this continuity example with the liquid accumulation. What we did was found the mass flow rate in, the mass flow rate out, and then used the difference between the two in order to calculate the rate of the fluid level rise. In this next example, we're going to be considering a tank where there's a piston moving to the left that's forcing water into the tank, a piston, smaller piston, moving to the left that's withdrawing water from the tank. And so what we're interested in here is what's happening to the water level over time. In other words, is the water level constant, meaning that the flow in is equal to the flow out? Is the water level falling, which would mean that the flow out is bigger than the flow in? Or is the water level rising because the flow in is bigger than flow out?
Alright, in this example there is a tank and it has a couple of pistons. There's a pipe with water going into the tank and pipe where water is going out of the tank, and these pistons are moving into the tank. Actually, and I've got the arrows backwards. The piston is moving into the tank from the right and out of the tank at the left. What we know is that the diameter of this is 3 inches and the diameter of this pipe is 6 inches. We know a little bit of information about the velocity of the pistons as they move. This piston that's moving outward from the tank it's moving at 2v compared to the piston that's moving into the tank is v. And so you can see that the diameter here is 1/2 the diameter. The pipe on the right is double. So what we're interested in is there's some water inside of the tank here, and we're going to use the Reynolds transport theorem of considering a control volume and looking at what's going into the control volume, what's going out, and how does the accumulation inside of the control volume change in response to what's in and what's out. And so the water is entering the tank here. This is where water is going into the tank, and here is where water is going out of the tank. And so we're going to calculate the mass flow rate in and the mass flow rate out, and then take a look at how the flow rate is changing. The water surface. Is the water surface rising, falling? And one thing I like to do is ask students just to guess based on intuition, if it's rising, falling, or staying the same. So, water level, does it rise? Does it fall? Or does it stay the same? And just to summarize, once again, the diameter of the pipe where water is going out is 3 inches, which is 1/2 of the diameter where the flow is going in. And the velocity out is double the velocity of the piston that's pushing water into the tank. So again, does the water level rise, fall, or stay the same? Well, the trick to this question, and inevitably I get quite a few students who will say, oh, the water level stays the same because the plunger going out may have twice the velocity, but it's got half the diameter, therefore it all cancels out. But that's not true, because remember that the mass flow rate is dependent on the density, the area, and the velocity, not the diameter. It's the cross-sectional area that depends on the mass flow rate. And so if we were to calculate the area of the flow that's going in based on a diameter of 6 inches, then the area is going to be pi d squared divided by 4. And so the area of that is going to be 28.274 square inches, whereas the area of the flow going out is going to be pi 3 inches squared divided by 4. And that works out to 7.07 inches squared. And so you can see that although the diameter doubled between the flow out and the flow in, that since area is a function of diameter squared, then the cross-sectional area is 4 times different. So that may change your sort of gut instinct on whether water level is going to rise or fall. We're going to write things in terms of these relative velocities. We don't know in absolute terms what the velocities are, but we can say that the mass flow rate in is the density of the water, the area in, and the velocity in. And so this being water, the density is 1,000 kilograms per cubic meter. The area in, we could convert that from inches into square meters, but in this case there's really no need to do that because we're just going to be working in sort of relative units anyway. So we might as well just leave it in 28.274 inches squared. As long as we're consistent in comparing the in and the out, we can get away with that. So what we have is 28.274 V. I'm sorry, I left the velocity. The velocity in is just V. So 28.274 V is the mass flow rate in. And so if we put the velocity in there, and we're going to have a real weird unit system, but this is all relative anyhow. We just want to know if the water level is rising, falling, or staying the same. We haven't been asked the rate at which they're falling, the rate at which things are changing, and we couldn't find it anyway because in this example we don't know the diameter. That's not specified. But that's okay. We don't have to know it to know whether the water level is rising, falling, or staying the same. So now let's consider the mass flow rate out. The mass flow rate out is the density, area out, the velocity out, And so again, it's 1,000 kilograms per cubic meter. The area out is 7.07 inches squared. And the velocity is 2 times v. So 14,138 v. Accumulation is in minus out. Or the way that we've looked at before is the change of mass in the control volume with respect to time is the mass flow rate in minus the mass flow rate out. So if we have the mass flow rate is 28,274 V and the flow rate out is 14,138 V, then the accumulation 14,136 V in. There's more in than going out, so the fluid level is rising.
So the water level is going up. In this final example, we're going to apply the continuity principles in order to find the velocity of water that flows around the sides of a cylinder as it falls down through a tube. So we've got a tube, or you can think of it as a pipe. The water is flowing upwards around the side of that cylinder as it falls downwards at a rate of 1 meter per second. And so the problem-solving strategy here will first be to select control surfaces and then identify the flow rate in and out of the control surfaces.
Alright, this is the example with a pipe, and inside of the pipe is a cylinder. And what we know about this situation is that the pipe has a diameter of 200 millimeters and the cylinder has a diameter of 150 millimeters. And what we're wanting to know is, in this case, if the cylinder is falling 1 meters per second, then what is the velocity of the water as it gets pushed around the side of the cylinder? The cylinder falls, it's pushing water out of the way, and so then what is the velocity of that water as it goes around the side? So just to illustrate, in a cross-sectional view, what we've got is a cylinder that we'll assume is falling right down the middle of that pipe, and the diameter of the pipe itself 200 millimeters, and the diameter of the cylinder is 150 millimeters. So what's the water here in the water velocity in that space, that donut-shaped space? So we're going to consider this using the Reynolds transport theorem, which says what we should do is set a control surface enclosing a control volume, and now consider the movement of things in and out of that control volume. In this case, selecting the correct control volume is a little bit tricky, and I'd invite you to try and figure out where you think you should draw the control volume in this case. Pause for just a moment as you think about that. Okay, so here what you want to do is have the control volume include the space where the water is going to be flowing out of, and then also the cylinder, because the cylinder moving into this volume is going to be pushing water out. So let's consider the flow rate of the cylinder into the control volume. And it's funny to think of something solid as flowing, but it's really the volumetric rate that it's entering the control volume. And so we'll consider what's going in to the control volume first. We want to calculate the area of the cylinder, so it's going to be pi d squared divided by 4. And the area of that cylinder, 0.01767 meters squared. Q, now again, it seems strange to be speaking about the flow rate of a solid object, but if we consider the velocity of the cylinder falling downward and the area of the cylinder, what that's going to allow us to know is the flow rate of the cylinder into the control volume, or how many cubic meters per second of the cylinder is entering the control volume. 1 meter per second is the rate that the cylinder falls, and we've previously calculated the area of the cylinder. And so it's entering the control volume at that rate. Now if we consider the exit, or what's going out of the control volume, we want to know the area of this tube, or the tube, pi d squared divided by 4. And in this case, the area 0.0314159 meters squared. What we don't know is the velocity of what's going through the side. In this case, B m to the control volume with respect to time is 0. That control volume is fully enclosed. If you consider what's going on inside of that enclosed tube, there's really no empty reservoir that can be accumulating storage. And so in this case, the rate of change is equal to 0. What goes in is going to have to go out. So there's no accumulation of mass in the control volume. So in this case, accumulation is 0. Thus, the in is equal to the out, or the mass flow rate in is equal to the mass flow rate out. Or, because it's well, we'll consider things in terms of the volumetric flow rate. The volume of what's going in equals the volume of what's going out. And I guess I ought to be careful when I say that, because for the mass to be conserved, then the density of that cylinder would have to be the same as the density of water. And we don't know that that's necessarily the case, but what we do know is that water's incompressible, and we'll assume the cylinder's incompressible, so whatever goes into the control volume, as that cylinder goes into the control volume, let's say if 1 liter of volume of that cylinder has entered the control volume, then it's going to push 1 liter of liquid volume out of the control volume. So really the governing expression is that the volumetric flow rate in is equal to the volumetric flow rate out. And that's what we're going to say when we calculate that the Q out, what that is the area in the side times the velocity in the side. And by the side area, what I'm talking about is the area that water is actually going to be flowing through is excluding that the cylinder that's going down. And so the water is coming up through this open area. And so we want to find the net space there. We found the area of the tube previously. What we also want to know is the cross-sectional area of the cylinder itself, which we've already found previously here. And so the area of the side is going to be the difference between the two. 0.0314159 meters squared minus 0.01767 meters squared. So the area that the water can actually flow through, 0.01374 square meters. And so the velocity through the side will be the flow rate, in equals out here, divided by the area on the side. 0.01767 meters cubed per second divided by 0.01374 square meters. So the velocity is 1.29 meters per second. And that's how quickly the water, on average, is going around the sides. That's the average velocity is of the flow as it shoots past the side of that falling cylinder.
Alright, so that concludes the falling cylinder example. If we just skip back to these announcements briefly and take a look at where we're headed and what we need to do, please remember to submit the report for lab number 8, which was the Venturi meter and Bernoulli's equation lab experiment, by 4 p.m. on Friday under my office door. I'm going to collect those and start grading them over the weekend. And you have until Monday, the 29th, to complete lab number 9. And then I'll collect the homework assignment 5A on Monday in class. So hope you have a great weekend, and please let me know if you've got any questions.